Okay, let's take a look at another functional equation. So this one is find all function f from natural number to natural number, which means positive integers, for which f of n is a square of an integer, which means perfect square. For all n is a natural number, and that satisfies f of n plus n equals f of n plus f of n plus 2 times n for all mn are integers, positive integers. So we can use the similar trick with as problem 1 we used. So first of all, in the original equation, we can substitute m and n to be 1, 1, so that we have on the left hand side we have f of 1 plus 1, which is f of 2, equals f of 1 plus f of 1 plus 2 times 1 times 1. So next we can substitute m and n to be 1 and 2, so that on the left hand side we have f of 3 equals f of 1 plus f of 2 plus 2 times 1 times 2. And then we have m and n to be 1 and 3, so that we have f of 4 equals f of 1 plus f of 3 plus 2 times 1 times 3, etc., etc., up to m and n is equal to 1 and k minus 1. So we have a f of k on the left hand side equals f of 1 plus f of k minus 1 plus 2 times 1 times k minus 1. So we can add all of them together. And then we know that we can cancel f of 2, f of 2, f of 3 and f of 3, f of 4 and f of 4 here. And then finally we have f of k minus 1, f of k minus 1 to cancel. So it turns out to be f of k on the left hand side, and we have totally k minus 1 equations. So for the first column, we have k minus 1 times f of 1, and then we still have another one here. So totally we have k times f of 1 plus the last column, which is 2 times 1 times 1 plus 2 plus 3 plus ... up to k minus 1. So we have a k times f of 1 plus 2 times 1 times k times k minus 1 all over 2. So 2 and 2 can be cancelled. So it will become k times f of 1 plus k times k minus 1. So we can just factor k times k out, so that it will be k times f of 1 plus k minus 1. So now we need to determine what the f1 is. So now we can make use of the condition f of n is a perfect square, which means that for all f of k are perfect squares, which means that we may write it as equals to, just say if we have f of let's say m is in an integer, is a positive integer. So f of m is m times f of k is a natural number. So f of 1 plus m minus 1 equals to n squared. So it is a perfect square. So it means that for all the m should be okay. So now we may strengthen this condition to be like, suppose p is a prime number. So that we have f of p is p times f of 1 plus p minus 1. Maybe we don't have this here. So it will be equals to n squared. So that, suppose this is a prime number, which means that p divides n squared. And if p is a prime number and p divide n squared, which means that p should divide this one, f of 1 plus p minus 1. Otherwise, we don't have p squared, so it will not be possible for the right hand side to be a complete square, to be a perfect square. So in this case, we can also find that p should divide f of 1 minus 1, because we just subtract this term by p. So p should also divide f of 1 minus 1. However, there are infinite many p's for all p's, but there are infinite many prime number. Which means that f of 1 minus 1 can only be 0. Otherwise, if f of 1 minus 1 is not equal to 0, then f of 1 minus 1 should be equals to p k from 1 to infinity. So it turns out to be infinity large, because all the p should divide f of 1 minus 1. The only possible way is f of 1 is equal to 1. Which means that f of 1 is 1. And then we can substitute this back to here. F of k is this one, which means that f of k is k times 1 plus k minus 1, which is k squared. So let's check. F of m plus n is f of m plus f of n plus 2mn. So on the left hand side, it will be nothing but m plus n squared. And on the right hand side, it will be f of m, which will be m squared plus n squared plus 2mn. So it is obviously m plus n quantity squared. So the final answer would be f of n is n squared. So this is the end of this video.